So we are actually done now with the basic finite difference. So today we peek into the beginning, at least, of a finite volume before we jump to fast solvers. We're coming back to finite volume afterwards with a little bit unstructured measures, stuff like that. So when we start now, we start very simple. We start with rectangular cells. To be able to define what is what, finite difference, finite volume, finite element. Well, finite difference is fairly easy to define, but the two other guys, they can sort of mingle. People are not often clear what they actually mean. Here I have stolen a little bit from Patankar's book from, when was it, 82, which you also have a copy of. It's an okay book to read if you are interested. So he defined it as follows. Finite difference, everything is based on Taylor series. That's not necessarily true. You can have polynomials, you can set up other schemes not based on Taylor at all. I think we saw it briefly when we look at the book of Verziger. You can have a peek there within finite difference. You'll see he also uses some Padé schemes, other schemes not based on Taylor series. But still finite difference. You are looking at discrete points in space, and you create derivatives by looking at differences then between the values in these points. Finite volume, finite element, more tricky. Historically, the finite element started from solid mechanics. They sort of glued the mesh to the material, and then when you had any deformation, the mesh followed the material, always. So that was the beginning. And then they formulated it using variational calculus, which is math I assume you haven't had. It's directly into Hilbert space. Some you need a functional that's sort of should now be minimized. Then the functional must then represent your original problem, which is very heavy math. I have not seen actually a complete functional covering the entire Navier-Stokes. So very heavy, very elegant if you can use it, but tough. So we are not going into this one at all. But here is sort of the birthplace for finite element. Now, engineers, they didn't like math, so they didn't use this approach at all. But you still get the same equation in the end by using the weighted residual. So weighted residual, sort of a large family, including what I will call both finite volume and finite element. So the philosophy goes as follows. You have an operator on your unknown whatever, pressure, velocity, and the operator, that's your partial differential equation. And then we define ourselves an approximative solution, again based on discrete points with some proper coefficients. And if you take your approximative solution and insert it into your partial differential equation, you will get something different from zero. You get a residual. And the aim is, of course, get this one as close to zero as possible. So since it's going to be zero on the other side, you can do whatever you want. And here we're using now a weight function, W. Multiply with this residual, and then we take a volume integral over some control volume in space. Can be anything. Again, since it's 0 on the other side, you can do whatever you want. No problem. So here, the weighted residual concept. So this one is what we are seeking. What this W is really doesn't matter, as long as it's not 0, of course. And now we differ between finite volume, finite element. So we split up the calculational domain into small control volumes, CV, with a control surface, CS. And for finite volume, we do it as simple as saying this weight function is 1 when you are inside the control volume of focus and 0 elsewhere. So you're only looking at one control volume at a time. And then you will be left with this equation. So volume integral is what we are seeking. Now, when you do this, typically what you do is define your space in nice volumes going next to each other. Of course you do that. So here you have one volume, here you have another one. And of course, if they have a joined boundary, that is of course very neat when you're now looking at not only control volume, but especially on the control surface. When you set up the equation system, you're going to have a lot of fluxes in and out of your control volume. Mass transport, momentum transport, energy transport, whatever. And then you know if something leaving one cell is going to appear in the other one. So it's very neat, very easy to get it consistent here, to get your scheme conservative, not losing anything. But nobody has said that you have to do this. That's not an absolute demand. Of course, it's practical, easy, but this is quite legal. You have one cell here, or one volume, and then another one, something like this. That's quite okay. That's not illegal. I mean, the equation system should cover any volume you might imagine. And even if you have a third volume here, it could be somewhere outside here. That's also allowed. Not easy. I mean, you're missing something. So calculating the fluxes in and out of this one will be quite impossible. But still, the equations should still cover such an isolated volume like that. Furthermore, you can let one of these move according to the other. So, of course, you will have some job in these double regions. You have a lot of interpolation, yada, 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 but still possible. So to have a sliding mesh in part of your system, yes, still an option. So don't limit yourself to something like this. Of course, here is where we start. Here is what we are going to do, but these would still be allowed. So don't limit yourself. As a first example, one-dimensional, what is it, a Poisson equation. If you let the thermal conductivity be constant, you can put outside, you have a double derivative equal to something. So, very easy equation system. And then I follow the notation started by Patankar, and everybody else in the world is using the same notation, so you might as well get used to it. You have a center point, and then you have neighbors, east, west, north, south, top, bottom, if necessary. So here only one dimension. The nodal points, they can be in the cell centers, but they don't have to. Here, more or less in the center, should be okay. The delta x's, you have one for the control volume here, and then another delta from center to center. So in a unstructured mesh or not uniform mesh is a lot of bookkeeping with these equations. Now, how to find the algebraic equation system? Well, here I have violated what I told you the first lesson. Here I have started with the partial differential equation, and then afterwards I integrate. You should never do that in that order. If you are going to use a volume method, you start with the volume, the integral formulation directly. So you set up your equation system here. Because the integral form, they cover more physics than the differential. Here you demand everything must be possible to make derivatives of. They have to be continuous functions. Here you're allowed to have a sudden jump inside the volume. That's okay. So start with the integral form if you're using integral equations. Don't ever use the differential form if you don't need it. Mathematically it should be the same, but it's this one little thing here demands continuous functions. Okay, the volume integral here, that should be fairly easy. You have it on a differential form, you have the derivative outside. So this is actually sort of a one-dimensional version of the divergence theorem. So you rewrite the volume integral of a gradient into fluxes. And here we are of course in trouble because somebody has to tell us on the small east, small west, that is on the phase boundary, what are the values here? And the values we then are searching for now is the derivatives. The source term can be whatever it wants. It doesn't have to be constant, it could be a function of the solution, could even include derivatives for that matter. Normally it doesn't. Normally you have at the most linear variation with your unknown, whatever that might be. So we have to now make a choice. How can we express these derivatives at these boundary phases? So our first choice, we say the temperature is constant when you are inside one single control volume. But that one doesn't really work. You have a constant value, a constant value, a constant value. Then you can't really define a derivative here. You have a sudden jump, so it's not a continuous function. So this won't work. Linear variation, not a problem. And of course here then we can represent a derivative at this point. That will more or less be from finite difference, taking the difference between these two and divide by the corresponding delta x. Very easy. If we are talking finite element, that's sort of my own definition, the difference between finite volume, finite element. Inside finite element, you can have quite complex behavior inside one single volume. With finite volume, we stop at linear variation inside one volume. Finite element could be very complex. Then you are going to need more than one point to describe what's going on, but that's a different story. So we are not covering finite element in this course. We limit ourselves into simple finite volume, maximum linear variation inside one single volume. So we create the derivatives, fairly straightforward, and we have now our algebraic equation, And here, if I have focused now on the center point P, I can easily from this equation rewrite it as a form Tp equal to, and then solve it iteratively if I wanted, or create a big equation system for all the different unknowns and solve the entire system. That's also an option. Patankar always look at the algebraic equation system in this form. You have the coefficients for the center point unknown equals, and then all the neighbors. And then you might even have a constant term coming from this guy, for instance, or depending on your equation system, of course. So this now will be our job, how to find a solution for such an algebraic equation system. Now, built into a lot of these codes, you can now actually see what is going on here. If you keep this method of positive coefficients, or the max-mean method, as I called it, if you keep that one in the back of your head, you see now the sum of all the coefficients now easily become 1. And then saying I demand all the coefficients positive, it's sort of very easy to implement into your numerical code. So it will be then very, very stable if you can do it. Depends on your equation, of course, if it's possible, but frequently it is. So the max-mean method is frequently sort of built into the program. Another example, one-dimensional convection and diffusion equation. So steady state, and here I say I know the velocity u, the viscosity is given, so my unknown is only this generic unknown phi. Exactly the same setup, and we integrate this equation, a volume integral, and then here I now need sort of the flux of this quantity at the western border and the eastern border. So we're going to need these two. And there is a problem, of course. We don't have the unknown located here. We don't have any phi here. So these guys, they have to be interpolated to be found. The double derivative integrated once will now be reduced to a first order derivative. So identical to the previous example, the derivatives at these points. So here we find these by simple linear interpolation, and when I've done it nicely, everything is in center. This one is located in the midpoint between these two. This will be only 1/2. Now we run into problems if we try to solve this directly using linear interpolation as such. Your equation system here. So no problem so far. And then we make it a very easy example. Let the velocity be constant. I mean, this one is given, it's not the unknown in the problem anyway. And of course, then let the viscosity be constant, and also the mesh to be uniform. The equation system will be reduced to something like this. So this is sort of the classical example that Patankar uses. Setting in numbers, and then you get something totally crazy. You set up 200 and 100 for the east and west point, and then you should have a solution sort of in between here, but you get something way off. And if you flip the values, you again get something way off. So the conclusion here is the central difference scheme doesn't work. It gives unrealistic results. So central differences, where have we used central differences that makes the problem? Well, that is for the convective term, of course. You need a velocity to decide what's the direction of the transport. So when you are talking central schemes versus upwind, it's where you have a velocity. So this one is quite okay with being a central scheme, not a problem there. But the first term, that's the one that makes the problem. Now let's see what he has done actually. What will the max-min method tell us here? Can we use it? Take the sum of all the coefficients. So we have this one plus this one. So here u half will fall, and we have 2 times of this term, which is exactly what we have here. So when you divide by this bracket, yes, you get the sum of the coefficient equals 1. Yes, you can use the method. Next, demand all coefficients positive. This one is positive, this one is positive, but this one, that's the problem. This one has to be positive. How can this be positive? Well, it can be positive if you rearrange a little bit the 2 up here. You just put an equal sign here. 2 goes up here, and then you have a velocity times delta x divided by viscosity. Then here you will get the cell Reynolds number. So the stability criteria here, the cell Reynolds number must be smaller than 2. That's what the max-min method tells us. And the number Patankar has chosen, you have a cell Reynolds number of 4. Of course it explodes. So that one is not fair, but of course it's correct. And for real problems, the cell Reynolds number might easily be hundreds. So central difference scheme, you can't really use it straightforwardly, no. So we have to do something. But in the 80s, early 80s, we didn't have much computers, so to find a solution at all, they made it simple. So Patankar jumped instantly to the first order upwind scheme. So the classic upwind. So just depending on the direction of the flow, is the information traveling to the left or to the right? That is the question, and then you define this value on the eastern border and the western border of your control volume. So here we now say the velocity is positive, and again viscosity and delta x be constant. You will have this recipe. And what now? Well, for the solution, yes, much more realistic. You'll have a value that will be bounded between these two guys, either way you flip them. So now he concludes the upwind scheme gives much more realistic results, and everybody's happy. And also here now, if you look at the max-min method for this scheme, the sum of the coefficients, you have 2 times of this one plus the u, which is exactly what you have here. So yes, the sum of the coefficient is 1. All coefficients positive? Yes, they are, no matter what you do. So it's unconditionally stable. So here you can have a cell Reynolds number of as much as you like. So, however, if you look at the correct analytical solution for this problem, you can tell this is actually not so good. So you are quite a lot of percentage away. So the first order scheme, the first order upwind scheme is terrible, very bad, very diffusive. Now actually we could have a quick check on this one, just for fun. Let's go back to the equation here. Let's find the modified equation for that one. The equation reads ddx of u, whoops, that was not a u. U phi equals, and then we had ddx of viscosity and d phi dx. And then you should take a volume integral of that one and then find your discrete equation system. Since we now have a uniform mesh, it will be identical to the finite difference scheme. There's no difference between those two at all. The philosophy behind them is quite different, but the end result, the algebraic equation system, will be identical. Here, of course, with finite volume, that's the strength. You don't have to use constant. Thank you. You don't have to use a constant volume. You can have different delta x's, delta y's. You can have unstructured meshes. That's not so fun with finite difference. But let's do the analysis. Find the modified equation for this one. Modified equation. How to do it? Well, first we are going to need a discretization scheme. So if I now do it the same way as we would have in finite difference, let's see, we have this one, center point, and then we had east, west, and then our cell is small east, small west. So we are sort of looking at the center point P here. So what do we get? Well, we can actually take the integral directly. Shouldn't be too hard. I mean, the only difference will be if you have the 1 delta x multiplied with the equation, or if you divide by delta x. That's actually the only difference you get. But here we had u phi located to the west minus u phi east equals, and then you have the same with the viscosity derivative to the west minus the same one to the east. And then we now choose an upwind scheme, saying my u, he is positive, going to the right. So the value here at the point west, he is actually coming from then the center point itself. So this one should now read u and center point, phi p, minus, and this one, u on the eastern boundary, then we take it to the left there also. That should now read phi east equals. And then we have normal central schemes for these two. You will have viscosity over delta x, and then the difference around the western point, that will now read phi west minus center point, and then here the same new delta x, and the difference here on the eastern boundary will be center point minus east minus phi east. So Now you see if you take this equation and you divide it by delta x, you will get exactly what we normally get when we are looking into the finite difference world. Never mind that. We are going to need some Taylor expansions for anybody outside the center point. So these three we have to provide with the Taylor series. So I mean, this is my point for finite difference. When you do the analysis, you go back to the finite difference world. So how can we express phi? We are going to need the eastern one. Well, there we have to use a negative Taylor series. So phi east equals center point minus delta x derivative, and then at the point p, actually, never mind that, plus delta x square half phi double minus third order. Phi w will be the same, but now plus delta x and plus and plus. So insert these into your scheme. What do you get? Well, for these two, put the u outside. What do we get? You have the center point minus this one. So the center point, he will fall, and negative, so he will become positive. So here you will have a delta x phi derivative. And then you will have minus delta x square half phi double derivative and even higher order terms equal. On the other side, we can take nu and delta x outside, and then what we have inside, well, we have something like phi w minus 2 times the center point plus the eastern points, as you can recognize from the double derivative in finite difference. So what do we get? The sum of these two minus 2 times the center point. So these will drop. You will have the west minus east. So you have 2 of him. No, sorry, both are plus. So these will disappear. But these will survive. You will have 2 of these. So you will have 2 times of delta x square half, and then double derivative. And the next one, here you have plus and minus, so the third term, he disappears, but the fourth term, he will be alive. So I will have something here with delta x 4, phi 1, 2, 3, 4. And then, of course, even higher order terms. So now that should be my modified equation. Now, is it consistent? Well, to make a consistency check, you should get your original partial differential equation back. And to see it here, you take the entire equation and you multiply 1 over delta x. Then what do we get? We will have delta x goes against delta x. So this one, that should now read u phi derivative, which is very nice. This one I throw on the other side. Then we have equal. another delta x here, so delta x square will fall, the 2 falls, and I will have viscosity phi double. So that was this one. Very nice. And then we have something in addition. This one, he turns up on the other side. So he changes sign, he will be positive, and he will be of order delta x. So delta x half multiplied again with phi double. And then I will have a term here. He will read something with delta x square, something. So there you have it. Yes, the equation here is consistent with my original partial differential equation. When you take lim, delta x goes to 0, you are left with the original equation. Okay. So the scheme is consistent. Also, the scheme is only first order accurate. This is the biggest arrow term you have. So it's the first order. Due to the first order upwind scheme, of course. The second order arrow comes from the double derivative. And here you can now see what has happened. This one you can join together in one phi double derivative, and yes, you have viscosity, and then actually you add something. Actually, I am missing a velocity here. He should be entering here somewhere. U. And here, U. So this is what you do with the first order upwind scheme. You add viscosity. How much do you add? Well, you can write it like this. Viscosity, and then you will have 1 plus the local cell Reynolds number divided by 2. So choosing a cell Reynolds number of 2, that's a stability limit for a central scheme, then you have double the viscosity. It's that bad. And if the cell Reynolds number is 100, you see for yourself, you are calculating a totally different fluid than you believed. You have a viscosity 50 times higher. So it's a very bad scheme. Any questions to that one? Modified equation, insert the Taylor series, check for consistency. You see the order of your scheme, and then possible to do some analysis here in the end. If we had done this with the central scheme, we would have ended up with something negative on this side. So it would be the problem there. To have the cell Reynolds number must be smaller than 2. You can do that one for yourself. Yeah, we're going to have a look into this false diffusion idea of Patankar, but I think we will do that after a break.